Okay, so this is the final part before the break. Julian's given a really nice overview of self-supervised learning methods where we have either an identity operator, so we're essentially doing denoising, or where we have operators that are invertible. So now we're going to start looking at the more challenging problems. What do we do when we've got operators that are not invertible? And there'll be two approaches that we'll take today. This morning, before the break, I'll talk about using multiple operators for doing the learning. And after the break, Julian's going to talk a bit about how we can use fundamental physical properties of the imaging problem to solve the same problem, but for a single operator. Okay, so let's just quickly return to where Julian left off. If we've got incomplete, so we're going to consider for now just noiseless, incomplete measurements Y. How do we do the learning? Well, as Julian mentioned, in terms of the shore, we don't see what happens in the null space. And in fact, it's very simple to write down a mathematical proposition that says that if I've only got access to measurements and I've got a single measurement operator A, then any reconstruction function f of y that takes the form of the pseudo-inverse of A applied to the data plus any function g that maps the measurements into the null space of A is going to be data consistent. So as Julian showed just now, if we have a picture of our cat with a null space, so it's missing the head, I can stick whatever I want in the head, and when I apply A, I will get exactly my measurements back. So this model is truly measurement consistent, but it's clearly giving me garbage in terms of predicting what is going on in the null space. And really, if we think about this should not be surprising. We basically observe no information of the signal in the null space, however many samples of measurement data we take. So this is not going to provide us with a solution. So how do we do this? And is there a way of doing learning from just measurements? And one way to do this is to, instead of and this is certain types of imaging. If we have access to multiple operators, so here I'm going to assume instead of my samples for training yi are, instead of just being a single A applied to xi, I'm going to imagine the scenario where I can change what the operator is for the different samples. So to give you a concrete example of that, we've already talked about MRI. Accelerated MRI, we take a subset of the Fourier measurements to do our acceleration. That would be something where we could choose which Fourier measurements to take, and that would give us an example of a multi-operator where the A depends on which Fourier component we take. So why might this be a useful thing to do? It might be useful because each AG now may have a different null space. And that offers the possibility, potentially, of doing learning using multiple measurement platforms. So to give you a sort of intuitive picture with respect to a standard in-painting problem, here I have a sample of a cat with some missing data. If my other sample had different missing data, so here we're missing this stripe, now we miss a different bit for this one. If I can put all these together, then potentially I can still learn my my imaging solution, even though each one of these has missing data. They have different missing data. So again, in the MRI setting, this would amount to in my spatial Fourier domain, taking one set of subsampling, maybe on a different image, taking a different set of subsampling, and then for the third image, yet another subsampling. So a simple necessary condition for such operators to provide, to enable us to do learning from just the measurements is that if I'm given a set A1 to A capital G of operators, these must essentially span the full space. So we can write this down as learning is only possible if the rank of the expectation over my different operators A transpose G A G is equal to the full space N. Okay? Now, and that immediately gives us a bound on how many measurements I need to take, or how many with respect to how many operators I have. Okay. And again, intuitively, you can think about this as if instead of having a different operator per sample, I observed every sample with all the operators. So now I'm basically stacking my operators together. If that operator still had a non-trivial null space, then I'm back to the setting of having a single operator with a null space, and we know that that is not solvable. So clearly, I need that the stacked versions of these operators must span the full space. And so roughly what we're saying is here in the, if again we think about this in terms of in painting, if I observe this block of pixels with one operator, this block of pixels with another, so on and so forth, when I add all these together, I need to span the full space. Okay, and another thing that we need to consider in the multi-operator learning is we now need to consider networks that explicitly take not just my measurements, but my measurement operator. So F has to act on both my measurements and my measurement operator A. Now, there are simple ways of doing this, such as filter back projection networks, illustrated over here, where all we do is we take my measurements, I apply either the adjoint or the pseudo-inverse of the operator to my measurements, and then I apply a generic deep neural network. However, one could argue that this might not be sufficiently expressive to cover these different settings. So other ways of doing it are unrolled networks, which, as I said, approximate or are inspired by iterative optimization algorithms that solve the penalized least squares problem and explicitly take the A in there. Okay, so maybe this is all we need to do. If we've got enough operators, if we've got, we've now got our neural network that learns both on taking in measurements and the different operators, can we use naive measurement consistency loss? And the answer is no. Naive measurement consistency loss, here we basically are just saying, I'm going to take the expectation over all my data and all my operators of y minus the projection back to the measurement domain of my prediction of y given that operator. But again, without noise, it should be clear that if I just choose my neural network function to be the pseudo-inverse of y for all the different AGs, so different on the different AGs, then I'm going to minimize that consistency loss and not get the required solution. So I need to do something more sophisticated. And you're not going to be surprised. We've already seen how to solve these things. We're going to basically replay Julián's talk on denoising, but doing it for the incomplete measurement operator. So let's first of all look at noise to noise again. And a paper by Liu et al. In 2020 introduced this notion of artifact to artifact. So artifact to artifact says, let's suppose again that I observe independent subsampling pairs. So I'm going to observe YA and YB, two different operators, capital A, little b, acting on the same signal and potentially with noise EA, EB, and we're going to assume that the operators are drawn independently from some probability distribution of sets of operators, and we're going to assume that the noise is drawn independently from each other. So in this setting, it's relatively easy to show again that taking the expectation where we predict the noisy measurements taken from one operator from the prediction made with the data from the other operator projected back. So we're predicting using the capital A, little a, but we're taking the measurements of that with capital A, big A, and we're comparing that to YB. Then that is essentially, in expectation, equivalent to a supervised loss where we're measuring just on YA, but comparing it to the actual ground truth X. And this is a supervised loss weighted with a weighted norm. So the Hessian here essentially is the expectation over B of AB transpose AB. So we see that if that expectation is full rank, so if expectation of AB transpose AB is N, then we have essentially a weighted supervised loss that is equivalent to the standard supervised loss and will have the same minimum when we optimize. If in fact we are choosing these two operators for this set of operators from an ortho basis, then it turns out you can actually do a reweighted version of these and directly get back. So you can basically do reweighting that turns this thing into standard L2 loss function. Okay, so two things to really stress here. One is, of course, as with the noise to noise, the independence assumption is hard to meet in practice. But the other thing I would like to stress, and this also applies to noise, when we say that we're achieving the equivalent of an MMSE estimator, we are equivalent to learning an MMSE estimator for one bit of the measurements we've got. So we've taken two sets of measurements, and we're saying I can get you the optimal MMSE estimator by throwing one of these away and just using the other one. So clearly, it's very far from optimal. I'm essentially halving the size of my data, my measurement data, in terms of doing my reconstruction. Okay, so do we also, how do we do this in practice, or are there other methods, given that doing this independence assumption is going to be quite difficult, drawing these things, having two looks at the same image? So another approach is to revisit the measurement splitting, essentially the cross-validation method that Julián talked about. And here, I'm going to talk about it intuitively in terms of in painting. So let's suppose that my A1 operator observes the bottom half of the image and the A2 operator observes the top half, but there's some overlap here. So I'm going to have some common set, a capital A, little a, that is observed by both. Well, clearly I can use my data in capital A, little a that I measure from that. I can train a network on that, project it onto A1, and predict the whole of Y1. And that essentially gives me the minimum mean squared error estimator of part of my image, but only the part belonging to that is observed by A1. I can repeat the process for A2, again using capital A, little a, and I predict the in this case, I'm just going to predict the Y2B. So here I was predicting the whole of the measured A. Here I'm now going to just predict Y2B. So I'm going to exclude the capital A, little a components of my measurements. And again, I can get my my conditional mean on that. And of course, because expectation is linear, I can then add my F1 star and F2 star and get the full conditional mean estimator. So the optimal minimum mean squared error estimator conditional on observations in observed by capital A, little a. This is great, but let me also stress that as with the noise to noise, I am not using all my measurements. And this is always the way with any cross-validation method, is that you end up throwing away data, throwing away predictive power in order to be able to do cross-validation. Okay, so how do we do this in practice? Well, in general, you can't see the key equations here, but in general, I'm going to generate multiple sets of measurements, and these measurements are going to be have the same have a component that is the same and a component that is different. Fantastic. So we have YA is some subset of YG, and capital A, little a is just my projection there. Same with YB, and I produce this this loss function, which again predicts the YB from the predictor based on YA. In MRI, this technique goes under the popular name of self-supervised learning using data undersampling, SSDU, and is a very popular method now for doing self-supervised learning in MRI. So it's subtly different from the noise to noise, so the artifact to artifact case. I am now generating something where this is true because I'm not doing IID sampling of my operators. I am producing a weighted supervised loss, but now I am the expectation of this loss is A transpose B, A transpose conditional on capital A, little a. So as with the as with the artifact to artifact, we have the same question. We need if this expectation is full rank. So now I need that conditional on the set that I want to build my estimator for. I need the rest of the operators to span the full space. Then again, I have something that's equivalent to supervised loss. I have the same minimizer, and I can, in theory, learn my conditional expectation for that mapping. I should stress that if there is noise in the data as well, so here we've set this out in terms of pure noiseless measurement operators, then I can replace this expectation term here with an appropriate Shor loss or one of the reconstructed loss that was discussed in the last part. And I should finally stress that although this is this condition here is sufficient in order to be able to learn this conditional expectation, it is not necessary. We'll see that when we look at the identifiability theory. Potentially there is more we can do to do better. Okay, so let's think about that now. Everything we've done with the cross-validation methods have basically used partition my data, so I throw some data away or I hold some data back in order to allow myself to do the training and still learn the structure. Can we use all the measurements? Because if we can use all the measurements, we should expect to get something that's substantially better and more powerful. Well, one way to do it that is essentially motivated by the identifiability theory we'll talk about later is, instead of just including my measuring consistency across my data, I'm going to introduce an estimator, an extra loss here that essentially says, if I build an estimator x hat from using the AG operator, then I want that also to be the same estimator I would have if I observed this operator x hat using a different operator AS. Okay, and it turns out that this is motivated, say, by the identifiability theory. So again, we can always replace the measurement consistency loss by a Shor loss, by a noisy version. So although I'm really presenting this in terms of noiseless, all this extends to the noisy setting again. But yes, the key thing is that we want this loss term here to try and enforce that f of AG of x, when measured through AG, is equivalent to the reconstruction we'll get with AS of x using AS. And the motivation for this is that we believe that most of our signals are low dimensional, and therefore we expect that all these operators give us a nice embedding of our measurement set, and so we can reconstruct. You'll note that in all the cross-validation stuff, although we get these nice probabilistic results, we're making no assumptions of that whatsoever. So we're merely learning the best we can from a sub-sampled set of data. Okay. So finally, this doesn't have the rank condition constraint, and we'll see when we look at the theory that this condition doesn't actually exist in the identifiability results. So finally, let me give a couple of examples. So we've talked about the maths, but let's actually look at how these things work in practice. So we applied this to subsampled MRI. So here we're now doing 4 times undersampling. The AGs are different subsets of Fourier measurements. We're using this is the Meta fast MRI data set with a single coil, if you know what that means from an MRI perspective. This is a knee, so the MRI of someone's knee. And when we do supervised training on all this data using an unrolled network, we get about 34.5 dB reconstruction, so dB higher is better. When we use SSDU, so measurement splitting, we get about 31.34, so it's good. It's better than, much better than doing just back projection. But when we use the multi-operator imaging, so the one that tries to use all the measurements together, we get 33 dB, so just 1.5 dB short of the Oracle supervised learning. And one final example before the break. We did this using, so this is comparing against a different method, which is called ambient GAN. So this is a generative adversarial network approach that also tries to learn from multi-operators. Here we're using a UNet, and we're just doing a toy in-painting problem. So we're throwing away a large number of pixels. This is the original image. Again, supervised learning is able to fill in most of the pixels and give us a PSNR of about 35.5. Ambient GAN using an adversarial network solution gives us about 29 dB, but again we're roughly 1.5 dB again off the supervised learning. So really, I guess the take home from this part of the talk is that there are methods either using cross-validation techniques or using these multi-operator imaging techniques that allow us to learn this thing if we have a sufficiently rich, diverse set of measurements that we can choose from. Obviously, that is only going to be applicable to certain inverse problems. Some inverse problems, you will only have a single measurement operator. Other ones, you will have access to lots of different measurement operators. So we're going to end here, but after the break, Julián is going to tell you about how we can still tackle some of these problems using clever techniques when we only have a single operator. Thank you.